Hello, we're the Eco PowerPuff Girls, and our project is called The Resistance.
We are 8th graders from the Young Women's Leadership Academy.
I'm Belisa Marquez, the project manager.
I'm Patricia Rodriguez, the project coordinator.
My name is Daily Buck, and I'm the research manager.
I am Alexa Burgoa, and I am creative design lead.
So our challenge statement description. The objective of our project is to design and construct earthquake-resistant structures out of economically and environmentally friendly materials. The proposed structures must be fabricated out of recycled materials like plastic, rubber, and adobe, and tested for durability. Both proposed structures and materials must show some ability to withstand earthquake movements. For our plastic structure, we produced this using plastic filament from our very own 3D printers here at school. For our rubber structure, we had to form this by hand using glue and rubber. For our adobe structure, this had to be formed using dirt and a straw mix to create a clay-like material. For our testing methods and mission statement, our structures were tested in an engineering lab with a machine that can simulate structural vibrations similar to an earthquake. Each test helped us determine which material provided the most flexibility, stability, and durability against a violent earthquake. Our results should provide insight on which reusable material might be most earthquake resistant, but also which material suits our goal of reducing carbon footprint here on Earth.
Our background research. Did you know it is estimated that there are approximately 500,000 earthquakes that are detectable each year? Approximately 100 of these earthquakes are categorized as destructive. Annually, earthquakes can destroy property, building materials, and infrastructure and cause billions of dollars worth of damage to our economic system.
These pictures here in the slide are buildings from around the world that are earthquake resistant, such as the Yokohama Landmark Tower from Japan, the US Bank Tower from Los Angeles, and the Transamerica Pyramid from Chicago.
For inspiration, in our research for real-world problems, our top search result was environmental harm. We agree with other scientists that our Earth is still in trouble and we're not doing enough to help. As members of our middle school student council, we constantly speak for working solutions in our community. We have started a recycling program, and this program has heavily influenced us to search for eco-friendly materials to build homes for this challenge. Let's find the solution. So for earthquake-proof structures, our research for this challenge has inspired us above and beyond. We discovered that both Japan and California built stronger, more resilient earthquake-resistant homes that last the test of time. We also uncovered that in Austin, Texas, they recently started to construct 3D printed homes made out of plastic and aggregate to make home building more efficient and eventually less costly. Is it possible to combine the cost and efficiency with earthquake resilience? Can our economy benefit from using other eco-friendly materials? Earthquake resilient homes and structures are more immune to destruction. Thus, the combination will help everyone. With guidance from our experts, we decided challenge would be best to test the following materials: rubber, plastic, and adobe as a possible alternative.
The experts we contacted. Most of our experts graduated from UTEP, and most of them work at TechSpot. So the first one we contacted was Arthur Aranda. He has a degree in Master of Civil and Environmental Engineering, and he is a licensed lab engineer. Then we contacted Elba Ortiz Enriquez, who has a Bachelor in Constructive Engineering and Management, and she's a construction inspector. And then we contacted Ozzy Garcia, who has a Bachelor's in Civil Engineering, and he works at Moreno Cardenas Incorporation, and he is a Senior Project Manager in Transportation. And then contacted Melody and Daniel Jimenez, who has a degree in Construction and Civil Engineering. They work at Atlas Technical Consultants, and they are licensed construction inspectors. Lastly, we contacted Elena Mascoro, who has a Bachelor's of Science in Civil Engineering, and her position is Engineering Assistant.
Our mostly important materials are rubber, 3D plastic PLA filament, hay, straw, sand, clay, concrete mold, and a stopwatch.
For our procedures, for the rubber procedures, we have to cut the rubber into 6 4x4-inch cubes. Using Elmer's rubber cement, we glued the rubber together into a cube. And as that rubber dried, we made the concrete using cement mix and put it into a 4x4 concrete mold. We let both dry for 45 minutes each. And once the time ran up, we put the model on top of the concrete and we had to glue that and let it dry for 36 hours.
The procedures for our Adobe model. We first mixed together the clay so it was in one large bowl. Then we would cut the hay to less than ½ inch and mix it into the clay. We would continue mixing while adding sand and water for consistency. We would add the sand and water as desired until they became clay-like. We put the clay into the 4x4 molds to shape them. Once they were dry, we would connect the molds into a cube/house shape. We would add Gorilla Glue to the edges if necessary. We would let it dry and put it on top of the concrete mold.
3D filament plastic. While using a Tinkercad, we 3D printed 4x4 0.5-inch square. Once they were done, we super glued fixed all adhesives to glue the squares into a hollow cube shape. We let that dry. We put the model on top of the concrete as a base. We also let that dry too. Seeing here, that is the machine that we use to represent an earthquake. While I am there and my 2 other teammates there are holding the models that we use to test.
The Gilson mechanical shaker. This is what we use to imitate an earthquake. And so what we first did was we put a paper plate under the model to imitate the ground. Second, we put the models onto the machine and then we clamp the model down using the plate and then turn the machine on as someone times the time steps.
So the Gilson mechanical shaker. It has a maximum sample volume of 1 foot cube. Its motion is a vertical vibration and the machine must be volted to the floor. It has 115 volts and 9.2 amps. The product's dimensions are 23 inches by 31 inches by 43 inches.
The Gilson mechanical shaker was used to represent an earthquake of a magnitude of 6.5 or higher. The lab. As we first stepped in, we had never seen or experienced these machines before. This was the lab that we used to test our models.
So looking at our data, the 3D filament plastic did last all the timestamps. The rubber and the Adobe last the same amount of seconds, but the rubber failed sooner than the Adobe.
So the results of our rubber test, the rubber model structure started to deteriorate at the 15-second mark. And sadly, at the end of 25 seconds, the structure completely collapsed and was destroyed. When we tested our structures, we decided to use timestamps to determine the stability of our models.
So as you can see here, this is our rubber structure and it's completely detached. And then the part where it's like the concrete, it almost got cut.
Here are some pictures we took during the testing, and we have a video to show you.
So the results for our Adobe test. Our Adobe structure survived the stimulated earthquake for 25 seconds. After that, our model sadly collapsed.
So here you can see the Adobe structure that's completely detached, and then the concrete is just shattered.
So these are pictures of our Adobe testing. As you can see in the bottom pictures, the model is clamped down using the paper plate. And we have a video showing the model on the Gilson mechanical shaker.
2, 1.
The results of the plastic structure. During tests, the plastic structure survived the longest amount of time on the Gilson mechanical shaker. Since it survived beyond the 45 seconds and remained completely intact, we decided to test it for strength. Using a compaction machine, we tested our model and it was able to withstand 2,050 pounds before failure. So this is our plastic structure, and when we tested it in the Gilson, the thing that was affected was the concrete, and then when we tested it for the strength, the thing that was affected was the actual structure. In the plastic, it cracked.
Here are some pictures and videos we took when we were testing for compaction and for earthquake resilience.
This is the compaction machine.
And here you can see these are some of the rocks that they let us have that we also tested in the compaction machine. After they tested our model, the rocks completely, they're all cracked because of how much weight was put on them in the machine.
They were able to withstand 6,000 pounds before cracking. So in conclusion, as a result, we found that using plastic as a building material alternative could be a workable option. In our tests, we found that plastic can form a strong structure that, while being exposed to violent shaking, could withstand earthquakes. Rubber is not a good alternative. Rubber materials are not economically feasible, and although we thought would be better, it still fails easily under simulated movement. Unfortunately, Adobe is not earthquake resilient to our tests. However, we believe it continues to be a good economical building material. Environmentally, buildings with Adobe can reduce our carbon footprint.
Further testing needs to be made to see what plastic and rubber will do for home building that takes into account that cold and hot weather, weathering by both rain and air. At the end, the whole team came out with bright new knowledge about how difficult it is to mine a medium that will protect us well, but producing it should not harm us.
After much investment of time and effort put into this project, as a result, we can now appreciate and apply our newly acquired information and learning to incorporate it into our real world and the engineering challenges we all face. If we were to continue our work, we would take advantage to deepen our understanding and experiment with more materials and machines.
This is us at the Atlas Technical Consultants, where some kind experts allowed us to use the Gilson shaker and the compaction machine to test our structures.
Pictures and videos were taken at the lab. As you can see, 2 of our models here are shown in this slide, being affected by the machine.
We would like to take time to give a big thank you to our teacher, Lee, who has helped us through this entire presentation and dedicated her time and effort into helping us all.
We are also grateful for the YWPN sponsors that make this experience a reality. We appreciate the time and support we received throughout this project. Your work and effort has been greatly appreciated. The Eco PowerPuff girls, thank you. We're now looking forward to learning about civil engineering and making this world a better place. Thank you.
Thank you.
Thank you.